Mabuhay everyone! Welcome back to our math class. We will have our final video for this year. We are going to continue our lesson on probability. However, this time we are going to focus on experimental probability of repeated experiments and making predictions. As we all know, right, for this lesson we need to accomplish three things. We need to finish watching the video so that we will understand the lesson. We will complete our guided notes and we are going to do our Alex activity to practice what we have learned. Okay, before we dive into our lesson, do you know that there is a time difference of 12 hours from Florida to the Philippines? I wake up early this morning at 4 a.m. to watch one of my favorite sports to play, which is volleyball. And I'm so happy that my team that I am betting for won the game. Okay, that's why let's learn this probability in a good way. So for today's lesson, remember that our goal is I can find the experimental probability of repeated experiments and I will make prediction using probability. Okay. Again, don't worry, this is our lesson and I'm very sure you got this one. So let's begin. So let us define first what is experimental probability. Okay, so we can use the result of repeated probability experiment to compare the number of favorable outcomes to the total number of outcomes. We call this one the experimental probability of the event. Again, let me emphasize experimental probability is the ratio of the number of favorable outcomes to the total number of outcomes in an experiment. Okay, so this is the fraction form for that, the ratio form for that. And you will be wondering, oh, this is the same for theoretical probability. It's also the number of favorable outcomes over the total number of outcomes. However, remember, okay, this is the results, okay, when you repeat the probability experiment. Okay, so we are doing the experiment not only one time, okay, but more than one. 500, 1,000,000, 10,000, okay, and by this results of this experiment, okay, we are drawing a probability based on our observation with the results. Okay, let me show you an example about that one. So let's go to our example number one. So the state lottery board is examining the machine that randomly picks the lottery numbers. On each trial, the machine outputs a ball with one of the digits 0 to 9 on it. The ball is then replaced in the machine. Okay? The lottery board tested the machine for 150 trials and got the following results. Okay? So the table shows the result. As you can see, we have our outcomes from 0 to 9 and we have here the number of trials. Okay, the total is 150 and for every outcome, we list down how many times each outcome appears. Okay, so using this table, let's answer these two questions. Letter A, we assume that the machine is fair. Find the theoretical probability of getting an odd number. Okay, so if you are going to find the theoretical probability, remember we are getting assuming that all outcomes are equally likely to happen. Okay, so we do not consider the number of trials. Okay, so for the theoretical probability, our total outcomes here is only 10 out of 10 from 0 to 9. Okay, so since we're looking for an odd number, so let's find out how many odd numbers do we have. We have 1, 3, 5, 7, and 9. So 2, 4, 5. So therefore here, to get our probability, we have 5 out of 10. And that will give us 1 half. That is a theoretical probability that when you use this machine, you will have a number that is an odd number. Okay, let's see the difference with letter B. From these results, find the experimental probability of getting an odd number. Express your answer to the nearest thousands. Okay, this time, okay, since we're looking for theoretical probability, we are going to count the number of trials. How many times our odd number appears in our 150 trials? We all know that our denominator is 150 because we have conducted the experiment 150 times. Now let's take a look at our outcome, which are odd numbers. So we have 1 appeared 12 times, 3 appears 18 times, 5 17 times, 7 14 times, 9 13 times. So if we need to find our experimental probability, we are going to find the sum of our favorable outcomes, okay, our odd numbers. So we have 12 plus 18 plus 17 plus 14 plus 13. Those are the number of trials wherein an odd number appear. Okay? And out of the total number of uh, outcomes, which is 150 out of 150 trials. So adding all our numbers here in our numerator, we will have 74 out of 150. Okay, since we're going, and then we need to simplify this one. As you know, we can divide both of these by 2. So therefore, it will become 37 out of 75. Remember, we have to simplify our fraction if possible. Okay. Since we would like to express our answer in the nearest thousands in a decimal form, right? You know that to get the decimal form, we simply divide 37 by 75. So therefore, 37 over 75 in decimal form is 0.493. Okay, it's actually 0.4933333. However, we are asked to round up to the nearest thousands, so it will just be 0.493. So therefore, as you can see, we have a difference. Okay, our probability for theoretical probability of getting an odd number is 1/2, which is actually zero point 0.5, right? 0.5, 50%. However, for our experimental probability, it's only 0.493. Roughly, they are close to one another because when you round up, okay, our 0.493, it will also be zero point 0.5. Okay, but that's the difference in how you get the theoretical probability and experimental probability. Okay, so we are going to dive more on experimental probability for our next example. So the spinner that we have here is spun twice. This experiment is repeated 250 times. The number 5 is spun both times during 4 experiments. What is the experimental probability of spinning 5 twice? This question is actually very easy, okay? Since as we can see, we're only looking for the probability that the number 5 will be spun both times, and during this experiment, it appears 4 times. So therefore, the experimental probability of spinning a 5 twice will just be 4 out of 250 because we have done the experiment 250 times. So to simplify 4 over 250, that is actually 2 out of 125 because again, we can divide by 2 because these two are even numbers and the GCF is 2. So as a decimal, we divide 2 by 125, and that is actually equal to 0.016. Okay? And if you want to change it into percent, remember the answer in our division, 2 divided by 125, then we just multiply it by 100 to change it in percent. So that will be equal to 1.6%. Okay? But I do hope that you know the technique. Instead of multiplying by 100, remember all you have to do is to move the decimal point 2 places to the right. So 1 and 2. So when you move the decimal point 2 places to the right, you're actually multiplying it by 100. Okay? So there you have it for example number 2. So we have our answers 2 out of 125 in fraction, 0.016 in decimal, and 1.6% in percent. Okay, so it's actually quite easy to find experimental probability. Okay, moving on. Let's say have example number 3. For example number 3, we have this table that shows the result of 500 experiments. Each experiment involved one person choosing one card from each of the two identical cards labeled 1 through 5. So, what is the experiment probability of a person A, B, C, and D? We're going to answer this one, okay? And we are asked to express our answer in decimal to the nearest hundred. Okay, so let's find the probability of choosing a 2 and then choosing a 3. So as you can see here, we have to look first for our first card and our second card afterwards. Okay, in our first card, we want a 2. So this is a 2, right? And our second card, we want a 3. So this is a 3. So looking at the intersection of 2 and 3, we have this number, 20. Okay, so that means that out of 500 trials, okay, a person will choose a 2 and then a 3 20 times for this experiment. So our probability is 20 out of 500. So simplifying this one, this is actually 2 over 50, right? And then since we're looking for the decimal answer, we divide 2 by 50. So our final answer will be 0.04. So the probability that a person choosing a 2 and then a 3 is 0.04. Okay, let's have question number two. What is the probability that a person will choose two fours? So once again, we are going to choose four in our first card, this one, and four in our second card, this one, and we try to see their intersection, this one. So 4 and 4 will be 17. Okay, so therefore the probability is 17 out of 500. Okay, we cannot simplify that one anymore because they are relatively prime. Their GCF is only 1. So we just change it to decimal. 17 divided by 500 is actually 0.034. So rounding up to two decimal places to the nearest 100, it will be 0.03. Okay, let's have example. Question letter C. Choosing a 5 and then a 3. So again, look at your first card, which is a 5, and then a 3 afterwards. Let's find our intersection. There it is. So you have 18. So that is 18 out of 500. So simplifying that one, we have 9 out of 250. In decimal form, that is actually 0.036. Rounding up to the nearest 100, it will be 0.04. And finally, for this question, we have choosing two ones. So this is our first card one. This is our second one. Look at that one. It's only 15 out of 500. Simplifying that one, that is actually 3 out of 100, dividing both side, both numerator and denominator by 5. And in decimal, that is 0.03. Okay, so having a table, all you have to do is analyze it, okay, to get your experimental probability. Okay, very easy. Okay, let's move on to question number 4. Okay, for question number 4, we are given this graph and we are asked to find, okay, the result of 200 experiment and find the probability that the person will roll the following sum. Okay, let's have the first one. I will just move this one so we can see it clearly. Okay, so what is the experimental probability of a person rolling a sum of 4? Okay, so looking at our graph, our bar graph. Okay, so the sum of 4 will be this one. Okay, and looking at the frequency of that one, we have 15, okay, outcomes. So therefore the probability that the experimental probability that the person will roll a sum of 4 will just be 15 out of 200. Okay, and here we're asked to express our answer to the nearest thousands and then express it in percent as well. So we have two answers. So 15 over 200 is actually 3 out of 40, and in decimal it will be 0.075. Okay, that's the nearest thousands, and in percent that is actually 7.5%. Okay, remember we multiply 0.075 by 100. Let's move on to our second question, an even sum. Okay, remember the even numbers are 2, 4, 6, 8, 10, 12. So we are going to add all the outcomes of our experiment wherein the sum is even. So this is our 2, okay, 4, 6, 8, 10, and 12. So we're going to add 5, 15, 25, 31, 16, and 3 to get our probability. So that is 5 plus 15 plus 25 plus 31 plus 16 plus 3 out of 200. So adding our numerators, our numbers in our numerators, that is actually 95 out of 200. Okay? In simplest form, that is 19 over 40. In decimal, that is actually 0.475. 0.475. So in percent, this one is actually 4.75%. Oh, 47.5% rather. I'm so sorry. Okay. That is, let me change that one. Okay. This one should be 47.5%. Okay. Because we have to move the decimal point two places to the right. Multiply by 100. Okay. Now let's have letter C. Find the experimental probability that our sum will be greater than 9. So this is our 9. So the sum greater than 9 will be the outcomes of 10, 11, and 12. So we will add 16, 8, and 3 out of 200. So 16 plus 8 plus 3 is 27 out of 200. We cannot simplify anymore because they are relatively prime. So in decimal, that is actually 0.135. So in percent, that is actually 13.5%. And finally, we're asked to find the experimental probability that the sum is less than 7. So this is our 7. So we will get all the sum that is less than 7. That is 6 to 2. Okay, so we will add 5 plus 9 plus 15 plus 21 plus 25 and all over 200. So therefore, there is actually 75 out of 200, and that is actually 3 over 8 in simplest fraction. Okay, and 3 over 8, okay, in fraction, okay, in decimal, okay, that will actually, I will put here, okay, so sorry, there's no space. So 3 over 8 is actually 0.375. In percent, that is 37.5%. Okay, so this is for letter D, the continuation for letter D. Okay, so there you have it. That is how we find the experimental probability, okay, having our experiments done a couple of times. Okay, before we move on, if you were listening a while ago during the first part of our video, if you know the answer, whisper to me. If you will be the top 5, you will have a prize, of course. How much is the time difference between Florida and the Philippines? And what is one of my favorite sports that I watched the game early this morning? Okay, just come to me and whisper the answer. Okay, moving on. Since we already know how to find the probability of our experimental to find the probability of repeated experiment, okay, now we're going to use our knowledge and probability in making predictions. Okay, we can use actually probability to predict, okay, the next thing that will happen. Okay, and as I've told you before, right, probability is very useful in making decisions. Okay, so you can use the theoretical probability of simple or repeated experiments to make predictions about future events. Because the theoretical probability of a simple or repeated experiment is the ratio of favorable outcomes to the total number of outcomes, you can actually use proportional, okay, reasoning to make prediction. We are going to use proportion this time, okay, in making our prediction, which will make our life easier. Okay, let's have our first example. Use theoretical probability to make prediction. So we know that the theoretical probability of rolling a 2 on a fair number cube is 1 out of 6. Okay? Based on this probability, how many times will a 2 be expected if the number is cube is rolled 450 times? Okay? So as we all know, our given theoretical probability is 1 out of 6. And we are going to use this one to find, okay, how many times our 2, right, will be expected. We represent that one as x, okay, when we roll it 450 times. So here is our x represent, okay, the number of times 2 will appear, okay, in 450 times. Okay, so as you all know, to solve our proportion, right, we go back on how we solve our linear equations. Okay, so we just cross multiply these two. Okay, cross multiply. So we have 6 times x, that is 6x equals 1 times 450 is 450. And as you all know here, we divide both sides by 6. So x is equal to 75. Okay, so therefore for this question, okay, the 2 is expected, okay, is expected to appear, okay, 75 times out of 450 times. Okay, So that is how we use proportional reasoning, theoretical probability in predicting, okay, our outcomes when we are going to repeat our experiments for a couple of times. Okay? Okay, that's very easy. Let's move on to our next example. So the theoretical probability of flipping a coin and landing on heads is one half. So based on the probability, how many times is the coin expected to land on heads if it's flipped 500 times? So again, we use our theoretical probability of one half when we flip a coin, okay? And then we are going to predict, okay, how many times our head will land, right? Over 500 times. So again, this one is X represent, okay, the number of times, okay, okay, head will appear, okay, when we toss our coin 500 times. So like what we did a while ago, let's cross multiply 2 times X, that is 2X, equals 1 times 5, that is 500. And then to solve for x, we divide both sides by 2. So x is equal to 250 times. Okay? So therefore, okay, when we do this experiment 500 times, our head will appear. The head, okay, is expected to appear, okay, 250 times out of 500 times. Okay? So 250. Okay, so that's very quick and easy. Okay, moving on to the next example. Example number 7. Okay, so the spin at the right is spun 50 times. LOD is spin at 2 8 times. Predict the number of times she will spin at 2 if she spin the spinner 600 times. And let's compare the theoretical probability, okay, of spinning the 2 and make our prediction, okay, between theoretical probability and our experimental probability. Okay, so since we spin the 2 8 times out of 50, so this experimental probability of spinning it 2 is actually 8 over 50. Okay, we are going to repeat our experiment 600 times, and we are going to find out how many times our 2 will appear again. Okay, so with this one, okay, we cross multiply again. Okay, so 50 times x, you will have 50x equal to 50x, 8 times 600, that is actually 4,800. Dividing both sides by 50. So our x is actually equal to 96 times. Okay, this is our experimental probability. Okay. Now, let's try to see the theoretical probability of spinning this spinner. Okay, so the theoretical probability, as you can see here, we have 1 out of 5, right? Okay, 1 out of 5. And we have that one, we will spin that one 600 times. We're going to find our number of times it will appear. Okay, so you have again cross multiply. So you have 5x equal to 600. We divide both sides by 5. So x is equal to 120 times. Okay, this one is our theoretical probability. Right? So as you can see here, right, our experimental probability is actually smaller, okay, than our theoretical probability. Okay, so that's how you compare the result of experimental probability and our theoretical probability. Okay, 1 over 5 is 20%, as you all know. So 600 times 25%, 20% is actually 120. Okay, and by the way, before I continue, I'll give you a clue for this one. If you have 8, this is only additional information, no need to copy this one, but I hope you will remember, right? 8 over 50 is equal to x over 600. We can actually cancel our 210 here, right? Because if you have this one, the technique is division, so we can use cancellation. So we actually can make that one as 8 over 5 equal to x over 60. And then you do the cross multiplication and you will have the same answer. You will have 5x equal to 480. And then you, so 5x equal to 480. When you divide that one by 5, it will still be equal to 96. So x equal to 96. Another technique is, as you can see here, right, you can actually cross out here one of our 0 and 0. So you'll have 480 divided by 5, and that is 96 times. Okay, let's move on to our last exam. Second to the last example. Okay, so a deck of 10 cards contains the number 1 through 10. The number 7 is chosen 8 times out of 100. Predict the number of times 7 will be chosen out of 750 times. And let's compare this prediction to the theoretical probability of choosing a 7. So let's find our experimental probability. So 7 is chosen 8 times out of 100. So 8 out of 100. And we're going to use this result to predict how many times will it appear out of 750 trials. Okay, so let's cross multiply again. So you have 100 times x is 100x. 8 times 750 is actually 6,000. Okay, then we divide both sides by 100. So therefore, x is equal to 60. So this is our experimental probability. Okay, so our 7 will appear 60 times out of 750 times. Now let's take a look at our theoretical probability. Since we have numbers, okay, the numbers 1 through 10, okay, the number 7 is chosen. So the probability of getting the number 7 out of 10 will actually be 1 out of 10, right? And then we're going to find out that 1 out of 750 times. Oh, should be equal. So we cross multiply, right? So that will become 10 times x, 10x. And then 1 times 750 is 750. Dividing this one, okay, by 10. So our x is 75. So when we apply our theoretical probability, right, okay, we can see that our 7, okay, will appear 75 times. So once again, our experimental probability is smaller than our theoretical probability. Okay, then finally, let's use that knowledge to answer our final question. Okay, for our final question for today. So Michael rolls a fair six-sided die 600 times. Use each box to complete the statement with the best prediction. Okay, so Michael will roll a 3 exactly or close to 100 times. Okay, so as you can see here, right, this is an obvious answer because when you say exactly, okay, we are very certain it will happen. So therefore, it's only probability, so we have to say close to because we are not actually very sure. Okay, so Michael will roll a 3 close to 100 times. Okay, why do you think 100 times? Remember, in the first six-sided die, right, there are six possible answer, and if you will divide 600 by 6, okay, if we assume they're equally likely to happen, each number will closely appear to 100 times. Okay, so Michael will roll an odd number again, not close to not exactly, but close to. Okay, Michael, an odd number. Okay, close to. So since out of 1, 2, 3, 4, 5, and 6, we have three odd numbers, 1, 3, and 5. And every odd number will be close to 100, like this 3, right? So 100 plus 100 plus 100, we can say that Michael will roll an odd number close to 300 times. Okay, half of our probability for this experiment. Okay, 600. Okay. So there you have it. That's how you find the experimental probability of repeated experiment and use that one in making predictions. Okay. I hope that the lesson in probability can help you in your future by looking at the numbers, being cautious on what's the probability of being successful in doing something. Okay, because remember, the higher probability, the more confident that you will be. Okay, so what do we do next? Of course, I hope you finish watching you finish your guided notes, okay, and you understand the lesson. So you are now ready to do your independent practice on Alex about experimental probability of repeated experiments and making prediction. Thank you so much, and I will see you again next time.